after shaft analysis with stress concentration, which is what we're doing in homework on module 4. We are moving, and you see homework 3 comes after this example because you should be doing similar to what you're doing here in the example. Shaft design is basically taking these equations and coming up with a design equation. Now, when I say shaft design, I really mean that we do not know what the shaft is going to look like. We do not know what material we're going to use. It's up to me as a designer to come up with a shaft profile or a shaft layout, geometric layout. It's up to me to choose a material that I can use to make this shaft. And I also, based on the dimensions that I'm going to choose for all the details of the shaft and the steps I'm going to come up with, I can provide or make sure it meets a safety factor requirement by calculating the design factors at different sections. And in order to do that, we simply take the Goodman Criteria equation. So when we calculated the shaft stresses, we were able to calculate a design factor. Without simplifying, you get equation 7,7. So you see here I have 1 over n is equal to sigma prime A over SE plus sigma prime M over SUT. In order to come up with this lengthy equation that looks a little bit overwhelming, simply all what we did is we applied what sigma prime A is here, the square root of sigma A squared plus 3 tau A squared. And here I applied sigma prime M, which is the square root of sigma A squared plus 3, sigma M squared plus 3 tau M squared. Please remember that sigma M is a 0 in most cases, and tau M is the one that has a value. Now, if you look at this equation, I have a design factor on the left side, and I have the diameter on the right side. We use this equation as is to find a design factor if I'm doing a shaft analysis. But if I am designing a shaft, I really want to solve for D. So in order to do that, we move D to the left side and move N to the right side. When we do that, I get equation 7, 8, which you see here, D was D cubed. So it is here, I take the cubic root of the quantity between these circular bracket in equation 7, 8. I like to mention that this lengthy equation 7, 8 can be reduced into this simple equation. D is equal to 16n over pi multiplied by 2 kf times MA over SE plus the square root of 3 kfs PM over SUT, and I take the cubic root of everything. Now, how did I come up with this? It's very simple. I know that MA has a value, TA is a 0, so this entire term is gone. MM is 0, so this entire term is gone. So I'm only left with KFMA and KFSTM here, which is what you see here, KFMA and KFSTM. Now, what is this telling me is that when you are designing a shaft, if you can find your MA and TM and start with some fatigue concentration factors, knowing an estimate of your fatigue endurance limit, SE, knowing your ultimate tensile strengths, you should be able to come up with D. Obviously, I cannot come up with a KF, an exact KF, an exact KFS, and an exact SE without knowing the dimension. So here comes the dilemma, how and where do I start? Some engineers with experience, if you're designing shafts day in, day out, you kind of, after looking at the loads, you probably can come up with some good estimate of dimensions that are going to work for this particular shaft. In general, if you're using standard geometry, we do have this table 7.1 that we can use for our first iteration estimates. for stress concentration, KT and KTS. And again, it's very important to read this warning. These factors are only estimates for use when the actual dimensions are not yet determined. And these should not be used once we have actual dimensions. Once we have actual dimensions, we should do like what I did in the example, using the tables from Appendix A15 and using the charts, figure 620 and 621, to look for exact values. So again, for typical steps, where D over D is around like 20%, so looking at the uppercase D divided by the lowercase d to be 1.2, almost, and using shoulder fillets that are sharp, where R over D is 0.02, I can use a KT of 2.7 and a KTS of 2.2. If you have a well-rounded shoulder fillet, then I can use for the bending 1.7 and 1.5. And please note that these stress concentration factor have a significant effect because they are, in some cases, they are more than doubling the stress. That's why I said for homework 3, you ought to check for A and C. Even though we know for sure that the bending axial stress is higher at point C, but should the KT be higher at point A, then maybe the location at A is going to become more critical or lead to the minimum design factor. But I think this is something that you can easily look at by knowing the dimensions as given in homework 3. We also have stress concentration factor for end mill key seats, when you have a key seat, and a sled runner key seat. And this is here is an extremely high for a rotating ring groove. We get a KT of a 5.0. Again, as you're going to see in the design example that I shared with you, this number changed significantly when we did the exact calculations. But this is for a first iteration estimate. So if I take you back to the design equation, now we know I can use table 7.1 to come up with KF and table 7.1 to come up with KFS. So after drawing shear and moment diagrams, you should have an MA and a TM at each critical section. And you should be able to use these MA, TM, KF, and KFS to go through a first iteration and look for a D. Some of you looking carefully here at the SE, the endurance limit. This also, especially the shape factor would depend on the diameter of the shaft. So this typically would be less than 1, maybe anywhere between 0.7 and 0.9. So you can start with an estimate when you're calculating an SE and then revisit. Remember, the design process is an iterative process. And that's why here it says first iteration. So it's like a loop in a computer program where we are going to start and then refine some of these values and keep going until we are happy. Until the answer is converging. I see no longer changes in the calculated diameter based on these stress concentration factors and the SE value. Okay, so these are the equations we're gonna be using for the shaft design. Does anyone have any question before I get into a shaft design example?
I have a question.
Please, go ahead, Jennifer.
So for homework 4, we have to use that equation that you just had on the board where D equals all of that. That's what we're trying. That's the equation that we're using for the homework.
Okay, let me put this back. For homework 4, and in doing your design, specifically for homework 4, we know for a fact that the shaft is rotating at a constant speed. So what I explained earlier about sigma A, sigma M, tau A, tau M is true. So this term is going to be 0. This term is going to be 0. So your equation may be simplified to this one right here.
Okay. And then, so we're given a torque in the problem. Is that the same torque that we use for this equation?
Let me open homework 4 so everyone can see it. So homework 4. We are given a motor provides a torque, right? And this motor is providing a torque, and this is, we're looking at shaft A. You see this shaft A. So the torque is being, read the problem carefully. The motor provides, in the double reduction gear train shown, shaft A is driven by a motor attached by a flexing coupling attached to the overhang. So it's attached right here at the overhang. So there is this input torque that is used to drive this gear, and which is driving the bigger gear attached to the other shaft. But we're primarily looking at shaft A. So I know that my input torque starts at the overhang, ends at this center line where I have my gear. So my torque is only present in this area. If you go beyond that, there is no torque, but there is still some bending moment. So as soon as you draw your bending moment diagram, knowing, of course, the forces, so you can calculate the forces, you can find where the critical bending moment is going to be. And if the moment is too small in this area, and you know that you don't have any torques applied, then you may focus on this area only where the torque is present.
Okay.
Jennifer? Yeah. Go ahead, Jennifer.
Yeah, no, thank you. And then one more question about the homework. So you had you just had the table up with the different first iterations for KT and KTS. Are we I'll wait till you pull it up.
Yeah. No, that's not the one. Okay.
So are we designing the type of, like, are we going to pick shoulder fillet? Are we going to pick end mill key seat? Or, because I don't think it's, is it specified in the problem that we have to use a specific?
Correct. Okay. Thank you for mentioning that. That's why in homework 4 here, I gave you a proposed design, and all what the comment, like instead of having each one of you come up with a geometric layout, I already gave you a geometric layout. The one thing I don't want you to use, I don't want you to use any of these diameters. So forget about these numbers for the diameters. I want you to solve for all of these diameters. So this is what you're going to be solving for. So you know that there is going to be a step right here. You know there is going to be a step right here. You know that there is going to be a key here, right? And you know that there's going to be another step here. So you know some of these, and these are the ones I want you to take into consideration. So let's say you find that this is a critical section. And what I'm referring here is the location of the bearing. So I'm looking at B, right? So at B, there is this diameter that they use as 1.574. I'm going to call this lowercase d. And then I'm going to have an uppercase d. And I'm going to say that, oh, this is going through a step. And because I'm using a bearing, if I want this to be leaning on the step, I may want to use a sharp shoulder fillet. So then this will lead me to use the 2.7 and the 2.2 when I am designing or looking to calculate the diameter lowercase d here instead of the 1.574. Does that make sense?
Yes. Thank you.
Good. Good. And again, I think luckily this problem is not as lengthy as the example because of the fact that the critical sections are kind of obvious. So you know like where you're heading, and then you may just carry over until you go back to the other bearing. But I'm really expecting you to come up with these numbers. And it's okay to have some of them the same. Any more questions on homework 4? Did you all get a chance to go over the shaft design example that I had posted?
I looked over the example, but it really didn't make sense to me.
Okay. Can we take, well, I think it may be useful then if we take the remaining time to go over that example together and make sure I answer any questions. Would you think that would be helpful?
I think that would be very helpful. Thank you.
Okay. Before I get started, if I may ask, I know we had this set from 8:15 to 9:30. Does everyone here have to leave at 9:30? Or if we need to go a little bit beyond that, are you okay with that?
Most days I had to leave at 9:30, but today my class got canceled, so I can stay.
You mean leave at 9:30, right?
Yeah, most days I would have to.
Okay. So for today, is it okay if I have to go a little bit after 9:30?
Yeah, that's
That
okay.
works. That works for me.
Yeah,
Okay.
I'm okay with that.
Okay. Now, again, please, let's all utilize this opportunity. If you have questions, please feel free to unmute yourself and interrupt me, because that's the purpose of having these kind of Zoom meetings, and give us really an opportunity to interact more, which I am missing. I think some of you are also missing. So let's make sure we make up for that by interacting here as much as possible.